Okay, so you're curious about machine learning, right? But maybe you're feeling a bit intimidated by all the hype around like these complex neural networks. I mean, we've all seen those diagrams. They look like something straight out of like a sci-fi movie.
Yeah, it can definitely feel like you need a PhD in computer science just to kind of scratch the surface.
Exactly. But what if I told you that some of the most fundamental principles of machine learning can actually be found in surprisingly simple models? And we're talking way simpler than those massive interconnected networks that we often see.
That's where Stephen Wolfram comes in.
Hmm.
He's been exploring these minimal models of machine learning, and what he's finding is very interesting and kind of mind-blowing.
And that's exactly what we're diving into today. We're going to try to strip away the complexity and see if we can like reveal the elegant heart of machine learning. And just a heads up, what we uncover might challenge some of your assumptions about how AI actually works.
Yeah, it definitely challenges the idea that we need to perfectly replicate the human brain to get these impressive results that we see.
Okay, so let's start with a familiar image, the traditional neural network. You know, the one with layers upon layers of interconnected nodes? It seems super complicated, but at its core, it's all about finding the right combination of weights and biases.
Yeah, think of it like this. Each connection between those nodes has a certain strength, a weight, and during training, the network adjusts those weights to kind of fine-tune its output.
So it's like finding the perfect settings on a sound mixer to get the audio just right.
Exactly. Now, Wolfram uses this interesting term, compiling a function into a neural network. What he's getting at is that the number of parameters, those weights and biases, impacts how accurately the network can represent that specific function.
So more parameters, more complexity equals better performance.
You would think so, right?
Yeah.
But here's where Wolfram kind of throws us a curveball. He suggests we can actually simplify things dramatically by rethinking that traditional network structure.
Wait, so instead of making those networks bigger and more complex, he's saying we can make them smaller and simpler. That seems a little counterintuitive.
It does. But that's where the elegance of minimal models comes in. So instead of those densely connected networks, Wolfram introduces us to this concept of mesh neural networks.
Mesh networks, what are those? Some kind of high-tech fishing net?
Not quite. Imagine a simple grid where each node is only connected to its immediate neighbors.
Okay, so much less interconnected than a traditional neural network. But can something that simple actually learn?
You might think that limiting those connections would hinder learning, but amazingly, these simple grids can still achieve impressive results.
Hold on, I need to wrap my head around this for a second.
Mhm.
You're saying that these mesh networks, with their very limited connections, can actually learn and compute complex functions, just like their more complex
They
counterparts.
can. And here's the really cool part. Because these networks are so much simpler, we can actually visualize their internal workings. So we can watch as data flows through that grid and see how the network processes that information. It's not just a black box anymore.
It's like being able to peek under the hood of a car and like actually see the engine running in real time. So instead of just trusting that it works, we can actually see the mechanics in action.
Exactly. And while we can see what's happening, it still raises some pretty fascinating questions. For example, does machine learning truly rely on those continuous fine-grained adjustments of weights found in traditional networks? Or is there something else going on?
Something even more fundamental.
Perhaps. And that leads us even further down this rabbit hole of simplicity into the world of discrete systems. But we'll save that for part two of this deep dive.
Well, okay, so last time we were talking about those mesh neural networks, you know, those simplified grids that can somehow still learn. It's like magic, but with less glitter and way more math.
Right, and we're about to dive even deeper into the magic, or should I say the elegance of simplicity. So remember how we were wondering if those like continuous fine-grained adjustments were truly essential for machine learning?
Yeah. Like, do we really need all that calculus to make these things learn?
Well, get ready for a surprise,
Yeah.
because we're about to enter the world of discrete systems. Um, think back to those old school cellular automata, those grids of cells that change color based on simple rules.
Oh, right. Like those mesmerizing patterns that kind of emerge from just a few simple instructions. But how can that kind of system possibly learn? It just seems too blocky.
That's the beauty of it. Even without those smooth curves and continuous adjustments, these discrete systems can still exhibit incredibly sophisticated behavior. Wolfram even draws this fascinating parallel between machine learning and like biological evolution to illustrate this.
Evolution. You mean like survival of the fittest, but for algorithms?
Exactly. Think about it. In evolution, you don't have tiny incremental adjustments. right? You have random mutations that are either beneficial or not.
So instead of like fine-tuning those weights with calculus, we're basically flipping a coin and seeing if the organism thrives or, well, doesn't.
In a way, yes.
Okay.
And this brings us to like a really crucial concept, computational irreducibility.
Okay, that sounds kind of intimidating. Can you break that down for me?
Okay, so imagine trying to predict the weather weeks in advance. You can't just skip to the answer, right? You have to let the atmospheric processes play out. That's computational irreducibility in a nutshell. Some processes are inherently unpredictable. You just have to let that computation unfold step by step.
So we're embracing a bit of chaos here. No more carefully crafted algorithm, just kind of let it run wild and see what happens.
Not exactly wild, but we are definitely shifting our perspective here. So it's less about finding that one perfect solution and more about like exploring the vast landscape of possibilities that kind of open up when we embrace this discrete, computationally irreducible world.
So we've got these simple systems and they operate in this kind of messy but fascinating way. But how do we even begin to navigate this landscape of learning? It seems like we're trying to find a needle in a haystack.
That's where Wolfram's concept of change maps comes in. It's like having a treasure map to guide our exploration.
A treasure map. Okay, I'm intrigued. Tell me more.
Okay, so imagine this. We have our rule array right. Each cell can pick from a set of rules, like
Wow.
AND or XOR. A change map would show us how tweaking a single rule, like flipping an AND to an XOR, would impact the entire system's output.
So it's like those choose your own adventure books, but instead of choosing the plot, we're choosing the rules of computation.
Exactly. And by analyzing these change maps, we can start to see which paths are most promising, which changes are most impactful, even in this unpredictable landscape.
So no more blindly following the steepest descent. No more calculus crutches.
Not necessarily. It turns out even in this discrete world, we can actually define something akin to derivatives. Remember those from calculus?
Oh boy, do I. Derivatives. Weren't those like squiggly lines on a graph? But how can we have derivatives if we're not dealing with continuous functions?
Yeah, it's a little bit of a mind bend, but just like we use derivatives in calculus to find the steepest slope, we can use a similar concept in this discrete world to identify like the most impactful changes. So we're essentially analyzing how flipping a single input bit changes the output. That's basically what a derivative tells us.
Okay, my brain is doing backflips right now, but I think I'm following you. So we're kind of borrowing tools from calculus and applying them to this blocky, discrete world.
Exactly. And this allows us to navigate that landscape of learning much more efficiently. It's like having a compass that points us in the right direction, even when the terrain is really rugged.
This is incredible, but it still makes me wonder, with all this talk about simple systems, what are the limits? How complex can these functions actually get? Can they handle anything that we throw at them?
Ah, that's the million-dollar question. And that's precisely what we'll explore in part 3. We'll uncover what kinds of functions these systems can represent and how these minimal models fare when we tackle tasks like language processing. Buckle up.
All right, so last time we kind of went down that rabbit hole of discrete systems and those fascinating change maps. It's like we're exploring this whole new dimension of machine learning, one where simplicity reigns supreme.
Yeah, and it gets even more mind-bending, because we're about to apply these principles to something that seems really, really complex, language.
Right, because last time we were teasing how these minimal models could possibly handle something as nuanced and intricate as language processing.
Yeah, it's easy to think that we need these massive billion-parameter language models to handle all the complexities of human language. But remember Wolfram's key insight. Machine learning thrives on harnessing existing complexity, not necessarily like replicating it from scratch. And language itself is already incredibly
Well,
complex.
yeah, we've got grammar rules and slang and sarcasm. I mean, sometimes I wonder how we even understand each other.
Exactly. And that's why those like traditional rule-based approaches to language processing eventually hit a wall. They just couldn't keep up with the ever-evolving, often messy nature of human language.
So how do we even begin to approach language with these minimal models? Where do we even start?
Well, remember those powerful transformer models we talked about earlier?
Hmm.
Their strength lies in their ability to analyze sequences like words in a sentence and understand the relationships between them.
Right, like seeing the words not just as like individual units, but as a part of like a larger interconnected web of meaning.
Exactly. And surprisingly, we can actually apply those same principles to build what we might call a minimal transformer.
A mini-me version of those language processing giants.
Precisely. Just like those transformers, our minimal version is going to encode each element in the sequence, each word, as a kind of unique fingerprint. But instead of using those complex multidimensional vectors, we're going super simple. Binary vectors, just strings of zeros and ones.
So we're giving each word a secret binary code, like a linguistic barcode.
I like that. Now, to analyze these binary encoded sequences, we use this really simple head that moves along the sequence, taking in a small chunk at a time.
Okay, so it's like our trusty rule-following scout scanning the sequence for patterns and connections. But instead of complex math, it's using those simple Boolean functions we talked about, AND, XOR, and so on.
Exactly. And just like that, we've simplified the core mechanics of language processing using those same principles we've been talking about all along. Simple rules, discrete elements, and letting that computation unfold organically.
This is really blowing my mind. But can this, like, stripped down transformer actually do anything useful with language? Can it, say, predict the next word in a sentence?
That's the real test, isn't it? And the answer, surprisingly, is yes. Even these minimal transformers can be trained to perform remarkably well on sequence continuation tasks.
Okay, I have to know. How do we go from, like, binary code and Boolean functions to actually predicting a meaningful word? It seems like a huge leap.
It's all about the translation. So after the head analyzes the sequence, its output, which is also just a string of rows and ones, needs to be converted into a prediction about the next word. We need a decoder ring.
We need to turn that binary gibberish into, like, understandable language.
Exactly. And for that, we can use another simple network. So we're essentially building a tower of these simple computational blocks, each one performing a simple task, but together they create something remarkably powerful.
It's like those intricate domino chain reactions where each domino only does one thing, but together they create something pretty spectacular.
I like that analogy. And that's the beauty of Wolfram's insights into minimal models. By breaking down complex tasks into smaller, more manageable chunks, we can begin to see how these powerful solutions can emerge from surprisingly simple elements.
So it's not about like perfectly mimicking human intelligence, but about leveraging the incredible power and efficiency of computation in new and often unexpected ways.
And that's what I find so exciting about this whole field. We're really just scratching the surface of what's possible with minimal models in machine learning.
So as we kind of wrap up our deep dive today, what's the one big takeaway you want to leave our listeners with?
I think it's simple. Don't underestimate the power of simplicity. The pursuit of ever larger, more complex models is undoubtedly impressive. But sometimes the most elegant and powerful solutions are hiding in plain sight, just waiting to be discovered in the beauty of simple rules, discrete elements, and the boundless possibilities of the computational universe.
It's a good reminder that in the world of computation, just like in the vast universe itself, the most fundamental ingredients can create the most profound complexity. Thanks for joining us on this incredible journey into the heart of minimal models. I don't know about you, but my brain is definitely feeling a bit more expanded.